this lecture, we'll look at 6 types of nuclear reaction. So in the last lecture, we looked at example of alpha emission. So this we just look at another example. So plutonium-239 is radioactive. It'll undergo alpha emission. So it's going to give off alpha particle. And so once you know that, then you can figure out what it decomposes to. So 239 minus 4, so 235. And 94 minus 2 is 92. So that would be the subscript, 235 the superscript. So then you just have to look at the periodic table. So element number 92 is uranium. So plutonium-239 would decompose to a uranium-235 atom and give off an alpha particle in the process. So 2 protons and 2 neutrons will be ejected from the nucleus of the plutonium-239 when it decomposes. Okay, so beta emission. So basically what happens in this case, so a neutron, so a neutron in the nucleus of the atom is converted to a proton and an electron. That's what this equation shows. And so this is going to stay in the nucleus. And the electron, of course, will be ejected. Will be ejected from the nucleus at a very high speed. So this is an example of a nuclide that undergoes beta emission, so carbon-14. So it will be converted to nitrogen-14 atom plus an electron. And so again, if you notice, the sum of the superscripts on the left must equal that on the right, and the sum of the subscripts on the right, so 7 and -1, has to equal what's on the left, 6. So, and the beta emission, the number of protons goes up by 1, and the number of neutrons goes down by 1, so the mass number stays the same. But the atomic number goes up by 1. So whatever element you started with, it'll be the next element in the periodic table that it's converted into. Okay, so positron emission, proton is converted to a neutron in the nucleus of that atom and a positron. So the neutron stays in the nucleus. So the neutron that's created stays in the nucleus, and the positron is ejected from the nucleus at high speed. So this would be an example of nucleus that undergoes positron emission. So technetium-95 will decompose to molybdenum-95 plus a positron. And again, if you notice, the sum of the superscripts on the right equals that on the left, and the sum of the subscripts on the right equals that on the left. So in the positron emission, the number of proton goes down by 1, so the atomic number goes down by 1. So whatever element's converted into will be the preceding one in the periodic table. And then, so since the number of protons goes down by 1, but the number of neutrons goes up by 1, the mass number remains the same. Okay, so positron emission has applications. So a lot of these nuclear reactions have different applications. So we'll talk about some of them. So one of the applications of positron emission has applications in medicine. So a PET scan, maybe you've heard of it before. So positron emission tomography. So basically what this can be used for is to image cancer tumors, for example. So how does that work? So one of the radionuclides that's used is fluorine-18. So it'll decompose to oxygen-18 plus a positron. So what happens to this positron that gets ejected? Well, it's going to collide with it could collide with an electron at some point. So if a positron collides with an electron, then they will annihilate each other, and they give off 2 gamma rays in the process. And so those gamma rays will be detected by a gamma camera. And then that's basically how you can use it to image a tumor cell, for example. So how does this work? So one of the ways to deliver fluorine to a tumor cell is this compound 2,18-FDG, which stands for 2-fluorodeoxyglucose. So this is the structure of the molecule. So this is carbon 1, 2, 3, 4, 5, 6. So that's a 2-fluoro. So fluorine 18 is introduced at carbon number 2 of deoxyglucose. And then this is administered in a water solution in an IV bag. So why is this molecule picked to deliver a fluorine-18? Well, because tumor cells, cancer cells are rapidly dividing, so they need lots of energy. So they take up a lot of glucose. So they take up this molecule, and so basically you deliver the oxygen-18 to the tumor cell, and the fluorine-18 to the tumor cell, and then the fluorine-18 undergoes positron emission. Positron that's ejected hits an electron somewhere, 2 gamma rays are created, and then the gamma camera can detect those gamma rays. So the fluorine-18 only has a half-life of 109.7 minutes, so that's pretty fast that it decomposes. So if you remember from the kinetics chapter what half-life is, so half of the material will be gone after 109.7 minutes, and then after another 109.7 minutes, the amount is cut in half again, and then again, so forth. So basically this molecule has to be created, synthesized by a chemist or somebody who has good chemistry skills, and then put into an IV bag and administered to a patient and do the PET scan all within a pretty short period of time. So that makes that a challenge, but the benefit, of course, is that it doesn't have a very long half-life, so it's eliminated from the body pretty quickly. And of course, the less exposure you're given to tissues, to radiation, the less side effects you're going to have. Okay, so electron capture. So what is electron capture? Proton and electron react to make a neutron. So this looks like an equation form. So a proton and an electron react to make a neutron and the nucleus of the atom. Okay, so this would be an example of a nucleus that does that. So potassium-40 will react with an electron, the proton in the nucleus of potassium-40 to create argon. So this is kind of what it looks like chemically. So if we just use the basic structure of an atom, so potassium-40 of course has 19 protons and 21 neutrons in its nucleus. And then in the first shell, it's got 2 electrons, second shell, 8 electrons, third shell, 8 electrons, fourth shell, 1 electron, right? Because it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So what happens is, so the nucleus is unstable. So what happens is one of these electrons in the inner shell goes into the nucleus of the atom. And then once in the nucleus of the atom, the proton and electron react with each other to create another neutron. So now you have only 18 protons, but now you have 22 neutrons, and you have a positron that's created that gets ejected from the atom. And now, of course, you have a hole, electron hole in the atom because the first shell only has 1 electron. So what happens also then in this process is that one of the outer shell electrons drops back down to an inner shell to fill that hole. And then in this case, an X-ray is given off. So if you remember that from Gen Chem 1, when the electrons transition from outer shell orbitals to inner shell orbitals, they give off electromagnetic radiation. And the energy of that radiation depends on how big the jump is that the electron makes. In this case, if it's a potassium-40 and it's one of the outer shell electrons moving to an inner shell to fill that hole, it gives off an X-ray. So that would be another reason why potassium-40 could be dangerous, because not only is it giving off positrons, it's giving off X-rays as well. And so then ultimately what you end up with is 2 electrons in the inner shell, then 8 in the second shell, 8 in the third shell, and the fourth shell has no electrons. So technically you made an argon +1 cation at that point. But again, a nuclear chemist would just write it as argon 40 because they don't worry about the electrons. But technically it's argon +1. Okay, so that would be an example of positron emission, or sorry, electron capture. Okay, so 2 more examples of nuclear reactions. So gamma emission. So basically this is just an unstable nucleus. That gives off a gamma ray, and this will typically be in a nucleus. In an excited state. So nuclei can be in excited states just like electrons can be in excited states. Okay, so an example of something that does this is 99M TC. So all of the isotopes of technetium are radioactive. So you actually, even though technetium is only atomic number 43, it's a relatively early element in the periodic table. You can't find it in nature because all of technetium is radioactive and it decomposes over time. So any technetium is synthetically produced in lab. So the symbol for gamma ray is that. So the M stands for it's a metastable state of the nucleus, so it's a nucleus in some excited state. And we won't go into more details of what that means. Okay, so this has medical applications as well. So one of the practical applications is renal imaging, or renal scintigraphy. That's how you say that. I don't know. I never heard of that word until I looked it up when I was making this lecture. So it's a radiopharmaceutical. So this is one of the molecules that is administered to a patient in order to do renal imaging. And so if you notice, there's the technetium 99. So again, in nuclear chemistry, all the nuclear chemists would show is their nuclear reaction, because everything else that's around it is just electrons and bonds, and that doesn't matter. That doesn't affect how the technetium, the radioactivity that it undergoes. But this is one of the molecules. It's maybe an interesting molecule chemically, especially once you've had organic chemistry, because this is a glycine, which is an amino acid. This is a glycine, which is an amino acid. This is a glycine, which is an amino acid. So it's a tripeptide that's coordinating the technetium. And this is, so those are all glycine molecules. And this one is what's called a mercapto, which is the S. Acetyl, which is the CH2 C double bond O. So that's just a chelating ligand that binds the technetium and then helps deliver it to the renal system. And then the technetium is radioactive, so it's excited to a metastable state. And then when it decomposes, it gives off a gamma ray. And then you have a gamma camera set up to detect those gamma rays. And since this localizes in the renal system, then that allows one to image the renal system. So I actually used to work with a chemist who, when he was in his postdoc, he discovered a good imaging agent based on technetium for the renal system. And it got patented, and then he ended up making a lot of money off of that because he gets money still today off of the royalties from that patent. Okay, so one more example of a nuclear reaction, spontaneous fission. So this is just a spontaneous decay. So spontaneous decay of an unstable nucleus to other nuclei. Okay, so if we take an example, so uranium-236 will undergo spontaneous fission. So it will decompose to yttrium-96, 39 plus an iodine-136 atom, plus 4 neutrons are ejected from the nucleus of the atom. So let me just write this again. Just to illustrate that, if you add up all of the superscripts, so 96 plus 136 plus 1 plus 1 plus 1 plus 1, you get 236. So the sum of the superscripts on the right has to equal the sum of the superscripts on the left of the arrow. And if you add up all of the subscripts, so 39 plus 53 plus 0 plus 0 plus 0 plus 0, then you get 92. So the sum of the subscripts on the right has to equal the sum of the subscripts on the left. So this could be, you know, so you could see a problem thrown at you like this. For example, maybe I didn't tell you what this species was. And you could figure it up just by taking 92 minus 39 to give you 53. So then you could look at the periodic table and figure out that this is iodine, and 96 plus 4, and if you take 236, subtract that, then you get 136, so you know what the mass number is of the iodine as well. Okay, so that is the 6 different types of nuclear decay reactions that we'll look at.